Okay, let's start main memory a little bit. We're not going to finish it clearly, but it's good to start. So what I'll do, I think I'll leave you early as opposed to taking a break. Is that good? Since we took a late break, maybe we can finish at 20 past. So 25 minutes. Okay, just shout at me if I'm going over because I'm not, I don't always communicate with that device. That doesn't tell me. Although I guess we could set an alarm. But I guess you're my alarm now. Okay, we're going to talk about main memory. We're going to switch gears a little bit. Caches are very important, of course, but we also want to look at something really important, maybe even more important going forward. Main memory and DRAM. And this is what I intend to cover. Clearly, we're not going to cover it in the 25 minutes. I'll give a broad perspective. We'll talk about DRAM fundamentals and operation. We'll talk a little bit about memory controllers. And then we'll go into latency, energy issues in DRAM and memory. So main memory, so I first some readings, I guess. This is a recommended reading. We wrote this paper with my PhD student Lavanya in 2014 or so. We need to update it, basically. But a lot of the things that are in this paper are still really important, except some of the more recent work is not included in that paper. So you can take a look at it. It basically covers a lot of ground on the memory systems and the research problems and opportunities. And there are some recent papers that I'm going to flash through. These are references for you if you're interested. This is very recent, actually. It talks about processing in memory, which we're going to cover. Well, I already said that. And we're going to, I think I already mentioned some of these. So, and this is a relatively old paper, but it's a short paper that basically provides a position on how memory should scale and what kind of approaches we should take going forward. Oh. And I think I mentioned this also, but let's see if we have time to cover solid-state drives. That's a fascinating area also. So there are some tools also, if you're interested. There are a lot of memory system simulators that we have in the group. We may have actually some assignment related to this, but maybe not this year. But if you're interested, you can take a look. Okay, so these are some required readings. Actually, you're going to read some of these. I think if you want to learn more about DRAM organization operation basics, I would strongly recommend that you look at especially these earlier sections of these papers. Because these sections of these papers are, I think, very clearly describe how DRAM operates, and it's very concise, so you can quickly get an idea of how DRAM operates. And we've already discussed the DRAM refresh basics. And we're going to cover also simulation at some point in these lectures, like how do you evaluate a future memory systems, and we're going to talk about simulators and different granularities and levels of simulation. You were doing RTL simulation, for example. It's not the best way of exploring the design space, but it's important at some point to get your feet on the ground, right? If you always do high-level simulation, you may fool yourself. We're going to talk about that. Okay, but let's start with why is memory so important, especially today? Because today it's extremely important, and everybody knows that we're constrained by memory. And everybody is trying to minimize the memory accesses because they know that when you go out to memory, it's not good. But people's hands are relatively tied because you may not be always able to minimize the memory accesses. And that's why it's becoming even more important, because computation is pushing the boundaries. I'll give you the performance perspective. This is Alpha 21264 we discussed just now, right? That's the machine that implements virtual multiporting. And also the physical copies, physical cache copies for the register file. Yeah, physical register file copies. So Dick Seitz was the chief architect of that alpha. And in Microprocessor Report, actually we can put up the link to that article on the website. He wrote a paper after this processor was released. He said basically it's the memory is stupid. In this paper basically he discusses, he basically essentially says we designed this processor such that it could finish 4 instructions per cycle. It's one of the fastest processors of its time. Actually it was faster than Intel's processors, especially in terms of clock cycle, 500 megahertz. It's supposed to finish 4 instructions per cycle. And then they measure performance. They figure out it's finishing 1 instruction every 4 cycles. Basically, it's operating at 1/16th of its peak bandwidth, right? Why? Well, it's waiting for data to come back from memory. And it had a very aggressive cache hierarchy at the time. You can read this, and there was also a paper by Rick Kessler that talks about the Alpha 21264 microarchitecture in IEEE Micro in 1999. We should put that up also. That's a beautiful description of the microarchitecture. And they put a lot of effort into the memory system, yet they still get 1/16 of the performance. Okay, that's 1996. This is my PhD thesis, which we'll talk about. I had proposed run-ahead execution, which is a way of tolerating memory latencies. And our motivation was basically this. This is a study that we did on simulation using Intel workloads, basically the workloads, many workloads that Intel used to design as processors at the time. Very varied workloads, all the way from CPU intensive to web intensive. And if you look at those workloads and analyze the performance, most of the time the processor is waiting for memory. This is 55% of the time you're stalled waiting for an L2 cache miss to be serviced. And you're doing some work, making progress, basically retiring instructions during this time. Okay, not a lot, right? Most of the time you're waiting for memory. Okay, and this is the paper, if you're interested. Oh, I don't have that slide, but there's another slide that's supposed to be here. Fast forward. Okay, I'm going to describe the slide. Fast forward, well, we're going to look at it later on actually, but somehow it's not here. That was, my thesis was around 2006. Okay, fast forward 2016, let's say Google publishes this paper in 2015 on their workloads and data center. And it's a beautiful paper. It describes the bottlenecks in their data center. And they look at how much time the processor is spending doing what. And they find that more than 50% of the time, the processor is waiting for memory in their workloads. In fact, their workloads are even more intensive. And about 10% of the time, the processor is retiring instructions, doing useful work. The rest of the time, there are delays that are indirectly caused by memory and some other things. So that's a span of just 20 years, right? And nothing has changed. The processors are still waiting for memory. And I can guarantee you that if somebody does that study 5 years from now, if something doesn't change, the processor would be waiting for memory. And maybe more, maybe a lot more. So during that time, processors have clearly improved, but we're wasting a lot of performance potential because we're not doing anything during that time. We're just waiting for memory. Okay. So that's the performance perspective. That's why memory is important. This is empirical data from many, many different folks. Let's look at the energy perspective also. So this is a slide from Bill Daly from his high-peak keynote. And as you can see over here, he basically shows what is the energy cost of doing different things inside a chip. Not everything, but some interesting things. I'll point out a couple of things. This is a 64-bit double precision floating point operation. It consumes 20 picojoules. This is a DRAM read or write. It consumes 16 nanojoules. And the difference between them is 800x. I took the liberty of rounding up 1000x because there are systems where this is 1000x. There are systems where this is lower also, but it's basically 2 to 3 orders of magnitude difference. Later we'll talk about some other studies that measure this, and if you optimize it, you get maybe 120x or so, which is still 2 orders of magnitude difference. So basically, this operation, it's actually complicated, double precision floating point. It consumes very little energy because it's on chip, whereas when you're doing a memory access, you're exercising those huge interconnects, and they're consuming a lot of energy. And there's a lot of energy also consumed inside the DRAM chip, and there's also energy consumed because of the conversion going from on-chip to off-chip as well. As a result, you get this 100 to 1000x difference in terms of energy. And if you look over here, there's some other interesting data. Going from one part of the chip to another part of the chip for a large chip, as you can see, 400 millimeters square, is about 1 nanojoule. Still about 16x difference, right, in that case. 1 order of magnitude. So going off chip is not good. Okay. So you can argue with all of these numbers, of course, and people try to improve all of these numbers. But this is improving, and this is also improving, but the relative difference is remaining the same. So it's good to ask the question right now, looking at this figure. Assuming you don't have a whole lot of locality in your system, does it make sense to actually, if you're doing a floating point operation, does it make sense to bring 2 items that are located in different places in memory, do the operation, and write it back to some other location in memory? You're doing basically 3 DRAM accesses to do very simple, well, relatively simple today, in terms of energy, computation. It may not make sense, right? You're basically exercising this huge disparity in terms of energy. Okay, so that's one of the motivators for doing something else. As opposed to processing here, maybe we should be processing close to the memory, such that we don't actually incur this huge energy cost, right? Okay, so reliability perspective, another issue. So basically, energy of memory is dominating a lot of things. I'll say one more thing over here. This actually didn't used to be the case if you go back 70 years ago or so. This was actually much more complicated than a memory access. It's hard to get exact numbers, but the cost of a complicated operation was about 2 orders of magnitude worse than a memory access at that time. Since logic has improved quite a bit, and we know exactly how to do these things, and Moore's law has enabled a lot of integration, of course. So we've improved this part, computation part, quite a bit. But over the course of 70 years or so, the interconnect and the memory part didn't improve as much. Interconnect certainly didn't scale very well. That's why interconnect, even on-chip interconnect, is a relatively large bottleneck, but off-chip interconnect is a huge bottleneck, right? Okay, let's look at the reliability perspective. So energy and performance of memory are limiting us today, but reliability is also very important. As we've discussed with Rowhammer, I'm not going to talk about Rowhammer in more detail, but these scaling issues that we have with memory is affecting our systems. And this is what I mentioned to you earlier also. Basically, the reliability of memory is reducing because things are getting too close to each other. And this is causing errors in the systems. And we already discussed this, as you know, earlier. Okay, so let me cover some trends, challenges, and opportunities in main memory in the remaining amount of time. So we're going to focus a lot on this part of the system, main memory. And you need some sort of working storage in whatever you design. Of course, it's huge in servers, right? It's huge in supercomputers, actually. It's important in mobile systems. A good chunk of the system is memory, but it's also true for many of the smaller systems. Well, I guess desktop is not smaller, but it's a small. How many of you have desktops today? Okay, that's more than I expected. How many of you don't have desktops and just use your laptop? Okay, that's increasing. If I asked this question 30 years ago, maybe the answer would be different, right? How many of you don't even have laptops? Okay, that's good. You don't do your assignments on iPhone or Android phone, right? Okay, but memory exists everywhere, and it must scale in many dimensions, like size, capacity, technology, efficiency, cost, and the algorithms we use to manage it to maintain the performance growth and the scaling benefits that we need from the systems. And it doesn't. Today we're attaching many things, right, to main memory: processors, FPGAs, GPUs, and heterogeneous combination of all of those. And some accelerators that I don't even put over here, video accelerators, for example. They all need memory, and they all contend for memory also. This is my cartoonish picture showing the importance of memory. Basically, if you look at this cartoonish picture, almost everything is dedicated to data movement and storage. Almost everything is the memory system, basically. Just the red parts, the core parts, are dedicated to computation. Everything else is moving and storing data. Or controlling the movement and storing of data. Caches, other caches, memory controllers, interconnects, memory, interconnects, and even bigger data stores, right? Basically, the takeaway is most of the system is dedicated to storing and moving data. And we've seen in the previous lectures that we built these hierarchies such that we don't actually go far away to get the data. But the design choices we made actually result in a system that looks like this. And if you quantify this, actually definitely more than 80% and more than 90% of the system is dedicated to structures that just move and store data. Even if you look at the cores, there's an L1 cache over here which is not depicted. There's a register file. There's a lot of interconnect to move the data from there, right? So most of the system, computation is very little actually. Even in GPUs today. GPUs are some of the one of the engines that actually has the heaviest computational power per area today. But even there, most of the areas dedicated to caches, interconnect, memory, other caches, and memory controllers. Okay, so I'll give you a couple of trends in the next few slides. Basically, there are some recent technology, architecture, and application trends that lead to some new requirements from the main memory system. That's one of the reasons main memory has become even more important, and that exacerbate the old requirements. We're going to talk about them. As a result, hopefully I've shown you with Rowhammer as an example, that DRAM and memory controllers, as we know them today, are unlikely to satisfy the requirements. That's why a lot is changing in the memory space today. And there are also some emerging memory technologies, like phase change memory, which we briefly discussed, that happen to be non-volatile, that enable some new opportunities, like manipulating persistent data directly inside the memory by merging the memory and the storage system. So given this, we need to rethink the entire main memory system and the systems we're designing around it to fix the issues we're having with memory technology and enable emerging technologies, and while satisfying all those requirements. So let's talk about some of these requirements first. So these are, in one slide, these are some of the major trends that are affecting main memory today. I think some of these are clear, and I don't have reliability over here, but they'll come in the next slide. But the need for memory capacity, bandwidth, and quality of service, performance is increasing. This is driven by the fact that we can do computation really easily. Basically, we can put many computation units on a chip, and we know how to design them reasonably well. Multi-core is an example, but this is also multi-agent, right? We can design accelerators, we can design cores, whatever. Those are really easy to design for us today. Of course, there are specific challenges inside them, but compared to memory, we know how to design them and fit them in logic relatively well. Applications are increasingly data intensive. There's an increasing hunger and demand for data. We've discussed this earlier. We're going to discuss it even more. And people want to consolidate things more and more on a single system. So if you have a single node, if you want to get the highest efficiency out of it, you would like to put many applications running together on top of it. This is true for cloud computing. It's true for mobile systems. You want to run many applications here at the same time, because that is good for improving efficiency of the system. In data centers, for example, if you dedicate one data center to run mail, that's not good because that goes underutilized. Even web search, that goes underutilized. So it's good to actually put other workloads on it, like user workloads, for example, and they get co-located. So you get much better efficiency in terms of energy, performance, energy, cooling, even area of the data center, as opposed to building 10 different data centers for 10 different workloads. Why not have one data center, right? I think this critically affects sustainability, for sure. So this is one example trend. Basically, this is data from an Iskra 2009 paper by HP Labs and University of Michigan. They basically plotted how fast the core count is increasing and DRAM capacity is increasing. So they're doubling at different rates, and core count is increasing much faster. As a result, they projected that memory capacity per core is dropping, or expected to drop by 30% every 2 years, which is not good because software has always relied on having more memory capacity to have more features in a thread, right? Now, you could argue, of course, with these trends. These are real data points that they had, but you could argue, okay, what about 2018 right now? You may do the study yourself, but maybe the trend is similar in GPUs, for example, especially. Maybe it's different, but now if the trend is different, you may actually want to ask the question, why aren't people putting more cores at the same rate? Well, maybe because they're limited by memory. Because if you cannot supply data to the cores, if you cannot supply capacity, it also makes no sense to put more cores, right? Okay, and trends are actually much worse for memory bandwidth per core, and we're going to talk about that. Memory bandwidth is increasing by about 10% every year. There are jumps, of course, like when we go to 3D stack technologies, which we will also talk about, but it's not good. Basically, we know how to design cores. We can maybe write this curve nicely, but we don't know how to supply the cores with memory capacity and memory bandwidth, with data, essentially. Let's have some fun with these trends over here. These are DRAM trends over the last 18 years. This is what's happened to the DRAM chip, basically. How much has its capacity increased? How much has its bandwidth increased? And how much has its latency increased? Any guesses? What do you think capacity will be in the 18 years? Yeah, I see that. Okay. Yeah, it's pretty much like that, except we're having trouble right now. Right. So it used to be increasing nicely, exponentially, as you can see. That's a log scale over here. And this is Moore's law, and enabled by Moore's law, but we're having also scaling difficulties at the circuit level. As a result, DRAM chip capacities are not increasing as fast. But they're actually not bad compared to this. So bandwidth has increased only 20x. This is also limited by power and other considerations. And we're not doing really well over here. So for latency has reduced by 30%. So we're going to talk a lot about latency, even though latency is very important, right? But this is easy to improve because of Moore's law. Now we are having difficulties even in those easy to improve things. Bandwidth is usually a function of money. You can throw more money at it, and it can get better, because you can actually have lots of channels, for example, right? You can have more pins. You can throw money at it. So this is not that hard to fix. Of course, cost is a very important consideration, so it's not that easy as well. Latency, even if you pay money, you may not be able to get it. So we're going to talk about latency a lot as well. So you need to have good system design and a lot of thinking to improve this. And partly this is because of the business model of how we design memories today, partly because of the mindset. The mindset has never been that latency centric. It has been more, okay, this business model is very good for capacity, so let's make some money out of it. I think this is, of course, a simplification of it, but there's a lot of truth in the way it affects mindset, right? So people are of the mindset that capacity is really important, but as a result, they may not pay attention to latency a lot. But latency is important. So these are some backward-looking applications, from my perspective, backward-looking, because they already exist. We know relatively a lot about them. And they're actually limited by almost everything. They need capacity, they need bandwidth, they need latency. So these are applications that are really driving the memory problems. But there are also new applications like genomics and machine learning that are driving the memory needs even further. Right? Okay, the next trend is energy and power in memory. This is a key system design concern today. This is a nice paper that we will put up by Charles Laferge and others at IBM Research, again, 15 years ago. They showed that about more than 40% of the entire system energy is spent on the off-chip memory hierarchy. Off-chip memory hierarchy including DRAM, off-chip caches, off-chip storage, off-chip interconnect at that time, 15 years ago. Today, well, not exactly today, but Power 8, IBM Power 8, about 8 years ago, they show that more than 40% of the entire system power is just in DRAM. Another paper that analyzes GPU power consumption shows that more than 40% of the system power is in DRAM. So a lot of things came on chip. DRAM has remained off chip, and most of the power is going there right now. Also, applications are intensive as well. And one of the issues that we've discussed that affects DRAM scaling quite a lot is DRAM consumes power when it's not used. You need to periodically refresh it. So you actually waste a lot of power just to refresh DRAM as well. Okay, so energy and power is another perspective. And I've already given you the relative numbers in terms of how much energy is spent for accessing memory versus doing computation, right? So on top of all of this, technology scaling is also ending. And Rowhammer is an example that I motivated this with. But there are other technology scaling issues in DRAM. And people have been projecting, ITRS, International Technology Roadmap of Semiconductors, has been projecting that DRAM, the feature size of a DRAM cell will not scale easily below some nanometers. And I like X over here because they like changing their projections, clearly. And people are pushing for lower X, clearly, to drive the capacity up. But it's true that there is a scalability limit. We'll see what that limit is, but it's become very difficult. So as you reduce the size of the cell, you get a lot of benefits: higher capacity, higher density, lower cost, lower energy, although this is becoming also more debatable with the change in with the end of Dennard scaling, which we discussed, right? Basically, DRAM scaling has already become increasingly difficult. And we've talked about some of these things. There are a lot of papers that we've written. And as a result, there is proliferation in the memory system design today. Basically, there are some emerging memory technologies like 3D stacked DRAM, reduced latency DRAM, hopefully lower cost ones, lower power DRAM, and non-volatile memory. There's a lot more. I didn't put everything. But if you look at the memory space, some of which we're going to cover, there are different types of DRAM and there are different types of memory also. And they have advantages, but they also have disadvantages. I'm not going to go through these detail, but the purpose of this slide is to show that we don't have a main memory technology, even in DRAM, that's good at everything. Right. Now, if you see this sort of picture, different technologies and different greens and reds, you can come up with a hybrid memory system. Right. But basically, this has been driven partly because of the scaling issues. And charge memories are becoming difficult to scale. It's difficult to place and control charge. This is the flash cell, which we may talk about later. It's also charge-based, but DRAM is charge-based. And reliable sensing becomes difficult as the charge storage unit size reduces with these memory technologies. And as a result, we have the DRAM scaling problem, which we have talked about in Rowhammer, right? This slide should be familiar to you. And as a result, we are having these reliability problems. And this is a paper that I would recommend that you read. It's not a required reading because we cannot make every reading required, but this is a very good example of the reliability trends in memory. And as we've discussed earlier in Rowhammer, it's important to build infrastructures to actually understand such issues. Not only reliability, but also latency, refresh. Well, refresh is a form of reliability, I think, but it's such a fundamental form of reliability, you cannot get away from that, right? Maybe errors you can protect, but refresh, yeah. If refresh is so fundamental to DRAM. And we built this infrastructure that I described earlier. So if you're interested in doing studies, we can talk about that too. And we've seen that because of these trends, you have these problems, right? Security problems also. So I'm going to skip these. And I talked about this paper. I don't know if we assign this as required reading, but clearly industry is very, very concerned about this also. People who don't normally talk to each other in industry are writing papers about it. Right? It's basically they're proposing co-architecting controllers and DRAM because we're having a lot of issues with memory. So we're at this point right now in memory. And this paper is proposing something that already exists. And they propose you should have error correcting codes inside memory because it's very difficult to tackle these reliability problems at the circuit level or the device level. So you'd better correct the errors when they happen with error correcting codes. So this error correcting codes occupy area inside the memory. You cannot use it. Basically, it's lost capacity. Right? That's one of the reasons capacity is not going to improve as fast because you're going to use some of that capacity for something else to correct errors. And this is already happening. Mobile memories have error correcting codes going forward, and I believe all of the memories will have error correcting codes if they're beyond some capacity. But if you if you went to DRAM manufacturers about 10 years ago or even 5 years ago, well, I guess 5 years already passed since this paper, so things are going fast. I guess I'm getting older. But if you went back to them, if we went to them 10 years ago and said, oh, I want ECC, error correcting code in your memory, they would kick you out of the room because they care so much about capacity. But now mindset is changing because there are other problems that are really driving things. Reliability is a huge issue. As a result, now they have error correcting codes inside the main memory. Right? Okay, and so basically we're going to talk about how do we solve the memory problem. And I'm going to give you 3 broad directions over here. We're going to talk about fixing it somehow, making memory and controllers more intelligent, just like that paper that I mentioned proposed, right? Co-architecting memory controllers and DRAM. This requires some new interfaces, new functions, and new architecture. I call this the system memory co-design. In that memory scaling paper that I mentioned, we called it the system memory co-design. We're going to talk about that. We're going to talk about another direction, eliminating or potentially minimizing it. Can we replace this technology that's having problems with some other technology, or maybe augment it? So this is going to take us to new technologies and system-wide rethinking of memory and storage and hybrid memory systems, which we're going to talk about. And we're going to talk about embracing it, potentially, maybe design heterogeneous memories, none of which are perfect, and map data intelligently across them. This opens up a new space in data management and maybe users. For example, some of your memory is very reliable, some of your memory is extremely unreliable, but some of your data doesn't care about being extremely unreliable, being on extremely unreliable storage, right? Because you can tolerate the errors at the algorithmic level. So in the next few lectures, we're going to talk about that. But keep in your mind that we're going to talk a lot about software, hardware, device cooperation. Because we're at this point in memory for various reasons. But one of the reasons has been we're so focused on improving one component or one part of the system, as opposed to having a more holistic view of the system and improving the system together with all of its components. And I think we're going to look at solutions that are really exciting from that perspective. And we're going to exercise some thinking across the hierarchy levels. Okay, this may be a good place to stop. You didn't stop me, but you should have stopped me 5 minutes ago. I guess it was interesting, that's why you didn't stop me. Okay, this is probably a good place to stop. We're going to pick it up and start with essentially some solution directions, and then go into more fundamentals of DRAM, and then do a lot of really interesting things in memory. I'll see you next week. Thanks.